Welcome to next lecture. In the previous lecture, we discussed effect of source inductance in single phase full converter and we did a few example problems, right? Now, let us recap from single phase ones. For example, consider there is an n pulse converter, okay, and at the load side, now I am going to draw output voltage waveforms for different categories. See what we discussed in our previous topic. Output voltage has two pulses from 0 to 2 pi, okay. Single phase, the maximum number of pulses we got it is 2 pulses. So this is a 2 pulse converter output voltage waveform. Now, for example, if I have an output voltage pattern something like this, okay. So in this particular case, what we can say, there are 3 pulses in the output voltage, okay. This is 2 pulse converter and this is output voltage of 3 pulse converter. Now one more possibility is, for example, the output voltage in one cycle, that is from 0 to 2 pi, it contains 6 pulses like this, okay. It contains 6 pulses. So this last one is referred as a 6 pulse converter. Listen carefully here. So from these 3 waveforms, what is the important point to understand? You just question yourself, which waveform is more nearer to DC? I can say the last one. 6 pulse converter output voltage is more nearer to DC waveform. Now follow carefully here. Yet the first stage of rectification, output voltage will have pulsating DC waveform, right? Pulsating DC waveform. What do you mean by pulsating DC waveform? It contains ripple component. It contains ripple component. Now what is the point here? This ripple component can be reduced with a filter circuit, okay. This ripple component can be reduced with a filter circuit. Basically the ripple component in the output voltage can be reduced by a filter which is placed at the load side, okay, which is placed at the load side. But what is the conclusion here? If number of pulses increases in V0 waveform, if the number of pulses increases in V0 waveform, then what do you mean by that? V0 waveform is more nearer to DC waveform, okay. V0 waveform is more nearer to DC waveform. Therefore, what is the benefit of that? If V0 waveform is more nearer to DC waveform, then we can say filtering requirement, okay, filtering requirement at load side, filtering requirement at load side will reduces. That is an advantage, okay. I am repeating, just if you read the statements step by step, you will understand. First stage of rectification, output voltage of any rectifier circuit contains pulsating DC. Pulsating DC will have a ripple component. That ripple component can be reduced by placing a filter at the load side. Okay. Suppose if the output voltage by the nature itself is more nearer to DC, then you can say that filtering requirement at load side will be reduces. How can that possible? That is by increasing the number of pulses in V0 waveform increases, it is possible. Now one more point is, when the number of pulses in V0 waveform increases, in the coming lectures we will see that some of the harmonics in source current will also not present. Okay, so what is another benefit here? If number of pulses increases, some harmonics in source current will be absent. Reasons we will study later. Okay, will not present at all. If number of pulses in V0 waveform increases, some of the harmonics at the source current will be absent. So if harmonics are present in the source side, what is the common practice? The common practice is, at source side one filter will be placed. Okay, at source side one filter will be placed. So size of that filter will be reduces. Size of that filter will be reduces. Therefore, what is the benefit here is, if the number of pulses in output voltage or in the converter operation increases, the benefit is some harmonics in source current will not present, right? So finally conclusion is, if the converter is operated with a more number of pulses, the filtering requirement at the load side as well as the source side will reduces. Okay, so how now the next question is, how can you get the more number of pulses in the output voltage? So for that the solution is three-phase, okay, by using three-phase rectifier circuits. So three-phase rectifier circuits, we can operate the converter with more number of pulses. So therefore three-phase rectifiers are best suitable for high power applications, because filtering requirement at the source side as well as load side will be reduces, right? Now if you recollect, in the single phase topic, while we are moving from half wave to full wave, we had a discussion. What is the reason to move to full wave rectifier circuits? Tell me. When half wave rectifier circuit source current has DC component, there is a possibility for source transformer to saturate. In order to eliminate that, we moved towards a full wave rectifier circuits. In the full wave rectifier circuits, we have studied various topologies. What are that? Full bridge and half controlled bridge, that is a semi converter. Now in that fully controlled or full converter circuits, what we have seen that source current waveform was square waveform and it contains all odd harmonics. Now if you operate the circuit with, instead of 2 pulses, if you operate with a more number of pulses, in the next classes we will see that some of the harmonics will not present in the source side, and load side output voltage waveform is more nearer to DC waveform. Therefore the conclusion is, three-phase rectifier circuits, by operating the converter with more number of pulses, filtering requirement at source side as well as load side can be reduces, right? So with this objective we will study three-phase rectifier circuits. Now instead of directly starting three-phase rectifier circuit, what we will do, first let us have some basic introduction. Okay, so what are different voltage representations and what are some different phase angles and all. So after getting clarity about these representations, then only we will start three-phase rectifier circuits. Now let us discuss basics of three-phase circuits. Okay, now here the source representation, see, until unless it is specified in the question statement, input for three-phase power electronic circuits, we can consider it is a star connected system. Okay, so this is what a source representation. Now let me take, this is a symbols A, B and C, right? Now what is the standard direction of rotation? That is anti-clockwise direction. For example, if you consider 3 persons are rotating in anti-clockwise direction, you can say the first person is A. After 120 degree, second person will start. After another 120 degree, third person will start. Therefore, with that notation, we can say the phase sequence is ABC. The phase sequence is ABC. The order in which these three waveforms will appear. Okay, next. Let us look into what is the definition of a balanced system. What is the definition of a balanced system? For example, there are three sinusoidals are given to you. It can be either voltage waveforms or current waveforms. When can you say the three sinusoidals are in balanced condition? That is, peak values, okay, peak values, or you can also say magnitudes, peak values of three sinusoidals, peak values of three sinusoidals are same. Next, all the three sinusoidals displaced equally, So whenever the three sinusoidals are having same magnitudes or same peak values, and in the total space angle, that is 360 degree, if the three sinusoidals are displaced equally, then you can say that particular system is under balanced condition. As the total angle is 360 degree and we have three sinusoidals, therefore 360 by 3 will give you 120 degree. Therefore, the thumb rule, whenever anyone is asking in interviews, what is the balanced system definition? Generally, people will jump onto neutral current is 0. Okay. Suppose if it is a delta connected system, it is difficult to define a neutral connection, right? So, in general, this definition is applicable for 3-wire system or 4-wire system, star or delta, right? So, the peak values or magnitudes of three sinusoidals is same, and the three sinusoidals are equally displaced in the given space angle, that is total angle is 360 degree divided by 3 will give you 120 degree between any two phase voltages or two phase currents, right? Now with these definitions, what we can do, first step, let us define phase voltages. So going forward, we will use this notation. Phase voltage means the voltage between one line and this common point, that is AO. Let us represent that. VAO is equal to VMP. Now follow the symbols carefully. V suffix MP. M indicates magnitude or maximum value. P indicates phase value. VMP sin omega t. Now going forward, for our analysis, we can take VAO as a reference. Therefore, the reference waveform can be represented with the phase angle is equal to 0. So VAO is represented with VMP sin of omega t. Next, VBO, VMP, okay, because we are considering with the balanced system. So VBO waveform also have same peak value as of VAO into sin of omega t minus 2 pi by 3. Now observe carefully here, phase B, okay, this is a displacement angles. Now phase B is displaced by phase A with a 120 degree, that is a lagging nature, and omega t is in radian, hence you have to substitute angle is also in radian. Of course, people used to say 120 degree, but at least while writing the equation, B, follow that omega t units are in radian, hence it is good practice to write angle in radian only. Next, VCO is equal to VMP. CO phasor is also having a same peak value as of BO and AO. Now we can write this CO phasor in two ways. Omega t minus 4 pi by 3. As I am representing with respect to phase A, CO lags AO by 240 degree or 4 pi by 3. In other words, if you see in this direction of rotation, I can also say that CO phasor leads AO phasor by 120 degree. Therefore, we can write it like this: VMP sine of omega t plus 2 pi by 3. Okay. So this is the phase voltages representation. Either of the way, CO you can represent in any one way. The next one is line voltages. Next one is line voltages representation. Okay. Now what is the line voltage definition here? V, A and B. So the voltage represented between any two lines. So how can you write here? VAB can be written as AO plus OB. In other words, VAB is equal to VAO minus VBO. Okay, VAO minus VBO. Of course, if you write down sin C minus sin D, you can get it simply. But here, let us use a phasor diagram. We can use it phasor diagram. So, what is that phasor diagram notation? Let us take, this is a VAO phasor as a reference, and VBO lags VAO by 120 degree, and VCO lags VAO by 240 degree in this way, or VCO leads VAO by 120 degree. Either of the way you will get it. Now what is VAB definition? VAO minus VBO. Phasor subtraction is not there, but we need to subtract it. What can I do? Extend this VBO phasor by 180 degree. Okay, then you will get minus VBO. Right, then you will get minus VBO. After then you can add these two phasors. You can add these two phasors. Then it will give you a phasor called VAB. Okay, then you will get a phasor called VAB. Now we can say that this phase angle is 30 degree. Okay, in this counterclockwise direction, what you can say, VAB phasor leads VAO phasor by 30 degree, isn't it? VAB phasor leads VAO phasor by 30 degree. Now I want to find what is the magnitude of VAB. What is the magnitude of VAB? How can you write? VAB is equal to, now this VAO, I can apply parallelogram law of addition of vectors. VAO square plus VBO square 2 into VAO VBO into cos of angle between these two phasors. Okay, so if the overall angle between these two phasors AO and CO is 120 degree, when you extend VBO by 180 degree, it will go in the middle of these two angles, right? Therefore, angle between AO and this minus BO is a 60 degree. So you can use that 60 degree here. Now this VAO I can use V phase square, VBO square can also written as V phase square. Now this is also V phase square. This 2 and cos 60 will get cancelled out. Therefore, I can write down here the relationship line voltage is equal to under root 3 times of V phase square. Therefore, we will get VL is equal to root 3 multiplied with phase voltage. Okay, root 3 multiplied with the phase voltage. So, of course, it is a very popular equation. You might study this, you might use this formula number of times in the machines and power systems course. But the reason in explaining here is this particular formula can be used for under two conditions. What is that? VAO and VBO are equal in magnitudes, and this 2 can be cancelled with cos 60. This is possible only when the phase angle between the original phases is 120 degree. Okay. Therefore, VL is equal to root 3 times V phase. That formula is applicable only for balanced system. Magnitudes of the three sinusoidals will be same, and the phase angle between any two sinusoidals will be 120 degree. Okay, under that conditions only line voltage is equal to root 3 times phase voltage formula will be applicable. Therefore, from this I can have two conclusions. One is line voltage have different magnitude with respect to phase voltage. Next, this particular VAB leads VAO by 30 degree. Okay, therefore by using this I can write VAB expression something like this: VML, where M indicates maximum value, L indicates line value, okay, into sine of omega t plus pi by 6. Okay, omega t plus pi by 6. What is the reason here plus? Because line voltage is leading the phase voltage by 30 degree. Okay, so I can write here plus pi by 6. Next, VBC definition: VBO minus VCO. VBO minus VCO. Let us see how to define that. Now from this phasor diagram, we want to have BO minus CO. Therefore, you just extend this VCO by 180 degree. Then you will get minus VCO. Now by adding these two phasors, then we will get VBC. Okay, VBC. Now if you observe carefully this phase angle, how much it is? How much it is? This is a 60 degree and this is 30 degree. Therefore, I can say this is 90 degree. Now follow carefully. Every phasor I am expressing with respect to reference phasor. What is the reference phasor here? VAO is the reference phasor, right? Therefore, VBC lags VAO by 90 degree. Okay, so I can write down that expression here as VML sine of omega t minus pi by 2. Omega t minus pi by 2. Okay, so BC phasor lags AO phasor by pi by 2 or 90 degree. Okay, that is what BC definition. Next, CA, VCO minus VAO. Okay, VCA is equal to VCO minus VAO. How can you define that? Now, CO and AO, where VAO, if you extend here by 180 degree, you will get minus VAO. Now, resultant of these two phasors will give you VCA. Okay, resultant of these two phasors will give you VCA. Now here, what is this particular phase angle? Just question yourself. VAO and minus VAO, this angle is 180 and this angle is 30. Therefore, what is this total angle? 210 degree. 210 degree is lagging or leading. That is, in this counterclockwise direction reference, I can definitely say that CA lags AO by 210 degree. Or in other words, in this way I can say leads AO by 150 degree. Okay. Now this is a 210 degree or this is 150 degree. Now let us write down in both the forms. What is that? VML sine of omega t minus 210 degree. How can you write 210? 7 into 30, where 30 means pi by 6. In other words, VML sine of omega t plus 5 pi by 6. Okay, 5 into 30 leads by 150 degree. So this is what a line voltage's representation. Now, if you observe carefully some important conclusions here. Now just look back into these waveforms, these phasors. Now here, what is the observation here? Angle between any two phase voltages is equal to 120 degree. Okay, that is the first observation. Similarly, angle between any two line voltages, this is also 120 degree. Okay, if you see here, angles between AO, BO and CO, that is 120 degree. Those are the phase voltages. Angle between any two line voltages, AB and BC, that is 120 degree. BC and CA, that is also 120 degree. AB and CA, that is also 120 degree. Next important point is line voltages, follow carefully, leads their respective line voltages, leads their respective phase voltages by 30 degree. Very important conclusion. Going forward in the rectifier analysis, this 30 degree is very critical. Okay. Now let us see that statement. AB phasor leads AO phasor by 30 degree. Okay. You should not refer with respect to minus VBO. Why? Because minus VBO is not the original phasor. Just for calculation purpose, it is extended version. Okay. Next, BC phasor leads BO phasor by 30 degree. BC phasor leads BO phasor by 30 degree. CA phasor leads CO phasor by 30 degree. CA phasor leads CO phasor by 30 degree. That means line voltages leads their respective phase voltages by 30 degree. Now here there are two groups of voltage waveforms are available for reference. Okay. There is no compulsory rule that you have to use only one particular group. What do you mean by group here? Phase voltages AO, BO, CO is treated as one group. AB, BC and CA are treated as another group, right? So you have to use any one group of voltages as a reference. There is no compulsory rule that. But just for ease of analysis, as per my knowledge, phase voltages group reference is preferable or easy for understanding to analyze half wave rectifier circuits. Okay. So for half wave rectifier analysis, it is preferable to consider VAO, VBO, VCO waveforms as a source voltage representation. Whereas for full wave rectifier analysis, line voltage references will be preferable. Okay, for full wave rectifier analysis, line voltages will be preferable. Again, there is no compulsory rule. For example, if I explain by taking line voltages as reference, and if you refer any book, in that book, if they consider phase voltages as reference, yes, still you can follow that. Okay, no one can stop you. But based on line voltages reference, full wave rectifier analysis will give you more clarity in understanding the waveforms. Okay, whatever the reference you take, whether I take phase voltage, you take line voltages, or vice versa, but if you take phase voltage for the same circuit and line voltage, both you just take, okay, you will notice that there is a 30-degree phase difference in the waveform point by point. Okay, only phase difference, but in the analysis at the end results, means average and RMS voltages, both calculations will give you same result. Okay, because circuit is same, it will deliver the same output. The reference of analysis is just for our convenience, but the circuit is don't know what waveforms you are taken as references. For a given circuit and a source voltage, it delivers the same amount of power whether you are taking as one voltage reference or another voltage as reference, right? So the concept is, for full wave rectifier analysis, it is preferable. I am not saying that it is a rule. It is preferable to take line voltages as a reference. For half wave rectifier analysis, it is preferable to take phase voltages as references. Next, let us write down the three basic equations under subheading fundamental component. I will tell you the reason. VAO is equal to VMP sin omega t. VBO is equal to VMP sin of omega t minus 2 pi by 3. VCO is equal to VMP sin of omega t plus 2 pi by 3. Okay, and let us put in one column. These are all a basic three-phase voltage waveforms when the frequency is a fundamental component. Now, I would like to write down the same set of equations corresponding to fifth harmonic component. Follow carefully, very important discussion. Fifth harmonic component. Then what you will get? VAO is equal to VMP 5 sin of 5 omega t, right? VMP 5 sin of 5 omega t. Follow the notation carefully. VMP suffix 5 indicates that the peak value corresponding to fifth harmonic component. And this 5 omega t, that means fifth harmonic component, what you need to do? Theta, fundamental theta should be replaced with 5 theta here. Fundamental theta should be replaced with the 5 theta. So, in the similar lines, VBO, I can write it as VMP 5 sin of 5 omega t minus 10 pi by 3. Okay, 5 omega t minus 10 pi by 3, because this total angle should be multiplied with the 5. Okay, next point. How can you write this 10 pi by 3? 10 pi by 3, it can be written as 4 pi minus 2 pi by 3. Okay, if you take an LCM, you will get 10 pi by 3 only. 12 pi minus 2 pi, that is 10 pi by 3, right? So 2 pi is one rotation, 2 pi is same as 0. After second rotation, 4 pi is again same as 0 in the sinusoidal waveform, isn't it? Therefore, what is the point here? 4 pi by 3 is just same as that of 2 pi by 3. I'm sorry, minus 2 pi by 3. Okay. Therefore, you should substitute here VMP5 sine of 5 omega t plus, now in place of 10 pi by 3, I would like to write minus 2 pi by 3. Therefore, minus of minus, I will have here plus 2 pi by 3. Okay. Similarly, VCO will be VMP5 sine of 5 omega t plus 10 pi by 3. Plus 10 pi by 3 can be written as minus 2 pi by 3. Okay, minus 2 pi by 3. So these are the equations, three basic equations corresponding to fifth harmonic. Okay, now let us look into components similar to seventh harmonic. I hope by this time you can catch the point what I am saying. Theta should be replaced here with 7 theta. Okay, so theta should be replaced with 7 theta, right? Now let us write down first VAO is equal to VMP7 7 omega t. VMP7 is the peak value corresponding to 7th harmonic into sine of 7 omega t. VBO is equal to VMP7 sine of 7 omega t minus 14 pi by 3. Sine of 7 omega t minus 14 pi by 3, right? How can you express 14 pi by 3? 4 pi plus 2 pi by 3. Okay. So 4 pi is equivalent of 0. Therefore, 14 pi by 3 is the same as that of plus 2 pi by 3. It is same as that of plus 2 pi by 3. So, how can I rewrite this equation? VMP 7 sine of 7 omega t minus 2 pi by 3. Okay, that is VBO expression. Similarly, we can write VCO is equal to VMP7 sine of 7 omega t plus 14 pi by 3. That is same as that of plus 2 pi by 3. Now, I will tell you the reason why we wrote all of these three set of equations. For example, if three sinusoidal equations or waveforms are given to you and the question is what is the phase sequence? Okay, so you can always start with the what phasor has phase angle of 0 degree, right? In other words, if they show in the waveform which one is starting from 0. Okay, so in this particular case I can take that is A. After 120 degree phase B, after another 120 degree phase C is coming. Therefore, for this particular representation phase sequence you can write it as A, B, C. Okay. Now, for the fifth harmonic component we can notice that phase sequence as A, after 120 degree C is coming, after another 120 degree B is coming. Now the phase sequence is A, C, B. For the seventh harmonic component what is the phase sequence? Again, it is a ABC. Very, very important conclusions. Suppose if we consider fundamental phase sequence is positive, fifth harmonic phase sequence will be negative. Okay, and seventh harmonic phase sequence is same as that of fundamental. Okay, seventh harmonic phase sequence will be same as that of fundamental. Not only fifth and seventh harmonic components. For example, if you look into a numbers corresponding to 6k minus 1 and 6k plus 1 in three-phase rectifiers, okay, this particular number pattern is very, very important. Not only three-phase rectifiers, later three-phase inverter circuits also we will get similar scenario where k is an integer here. Suppose if k is equal to 1, what is this number? 6 minus 1, that is 5, 6 plus 1, that is a 7. Okay, next. Suppose if k is equal to 2, 12 minus 1, that is 11, 12 plus 1, that is 13, right? Suppose if k is equal to 3, 18 minus 1, that is a 17, and 18 plus 1, that is 19, and so on, right? So the harmonic which is of the number 6k minus 1 means 5th, 11th, 7th harmonics, 17th harmonics will introduce negative phase sequence. Okay, 6k plus 1, that means 7th, 13th and 19th and so on. These harmonics will introduce positive phase sequence. Now, if you look into odd multiples of 3, what are that? 3, 9, 15 and so on. Okay, basically three-phase rectifier circuits, three-phase rectifier and three-phase inverter circuits generally will not have even multiples of 3, right? So these numbers are referred as triple N harmonics. Some new terms are coming here. Triple N harmonics. Okay, odd multiples of 3, those harmonics are called triple N harmonics. Generally, we will see the reasons later in three-phase rectifiers and three-phase inverter circuits. Basically, I can say three-phase power electronic circuits, triple N harmonics will not present. Okay, reasons we will study later. And hence, these harmonics are represented as zero sequence components. These harmonics are represented as a zero sequence components. In power system fault analysis, we will study that whenever the system is deviated from the balanced conditions, such systems, means unbalanced systems, will be studied with the sequence components, positive, negative and zero sequence components. Another reason what is not discussed in the power systems course, that is effect of harmonics. Due to harmonics, these phase sequence components, means positive, negative and zero sequence components will come into picture. Okay, when these negative, especially negative sequence components are present, what are the impact on the system performances? We'll discuss that. So here at this stage, what we can say in three-phase power electronic circuits, generally the harmonics present are either negative or positive phase sequence components, right? Negative sequence harmonics are 6k minus 1 numbers, 5, 11, 17 and so on. 6k plus 1, 7, 13, 19 and so on. These harmonics phase sequence will be same as that of fundamental component. Let us discuss the effect of harmonics on the system performances. For example, suppose there is a DC motor, okay? It is rotating in clockwise direction. Listen carefully. One practical example, what is the impact of these harmonics, right? Just listen, try to understand. There is a DC motor it is running in a clockwise direction. Objective is we need to reverse the direction of rotation. Generally, what is the procedure? We will interchange either field terminals or armature terminals. That is a procedure for DC motor. For example, there is a three-phase induction motor. There is a three-phase induction motor. Okay, it is rotating with. Okay, it is supplied with a phase sequence of ABC. It is supplied with phase sequence of ABC. Let us assume that it is rotating in a clockwise direction with this phase sequence. Now, we want to change the direction of rotation for this three-phase induction machine. What we can do here, change the phase sequence to ACB. Therefore, the machine will now rotate with the counterclockwise direction. The machine will now rotate with the counterclockwise direction. If you really want to change the direction of rotation, that is the procedure. Okay. If you really want to change the direction of rotation, you can interchange the phase sequence. Now, before moving further, let us have a basic working principle statement. For example, when a three-phase induction motor stator, okay, stator is generally in the distributed three-phase winding. If a three-phase distributed stator winding of this induction machine is supplied from three-phase balanced source, for example ABC sequence, then what will happen? A rotating magnetic field will produce in the area. When that rotating magnetic field cuts the rotor winding, and if the rotor winding has a closed path, how that closed path is? Either through short circuit in squirrel cage mechanism or through some external circuit in a slip ring mechanism. So either of the way rotor winding has a closed path, then what will happen? Some rotor currents will start flowing. Due to the interaction between the air gap magnetic field and rotor currents, a torque will produce. Okay, so that is a basic working principle statement of three-phase induction machine. So in that working principle statement, the point to underline is this three-phase distributed stator winding is excited from three-phase balanced supply. Okay, three-phase balanced source voltage. But instead of giving three-phase balanced source voltage, now this three-phase induction machine is operating from some power electronic circuit, for example. Okay, output voltage of this power electronic circuit has a three-phase voltages. So power electronic circuit means due to switching operation, we can say V0 here is not pure sinusoidal, right? This V0 contains one fundamental component of frequency F plus fifth harmonic component plus seventh harmonic component. Okay, seventh harmonic component. Now, if this induction machine is connected from a three-phase power electronic circuit, whose output voltage of this three-phase power electronic circuit contains fundamental fifth harmonic and seventh harmonic components. In that cases, what is the impact of these harmonic components on this machine performance? Okay, let us see it carefully. So, fundamental component has a phase sequence, for example ABC, will produce an air gap field which will rotate in clockwise direction. Okay, any one direction you can assume. Let me assume it is a clockwise. So fifth harmonic component will produce an air gap field which can rotate in counterclockwise direction. Why? Because fifth harmonic component has a phase sequence of ACB. Next, seventh harmonic component will produce an air gap field component which will rotate in the clockwise direction. Okay, because seventh harmonic component phase sequence is ABC. So now in the air gap field, just think about it. It is not a balanced sinusoidal. It is the resultant of fundamental, fifth harmonic and seventh harmonic components. Very, very important conclusion. If at all three-phase induction machine is excited from three-phase balanced source, it will operate whatever the theory you will study in the books. But if this three-phase induction machine is controlling from power electronic circuit, whose output voltage is not a balanced pure sinusoidal, it is having harmonics. Under that condition, the air gap magnetic field is not pure sinusoidal. It will have distorted sinusoidal flux in the air gap field. What do you mean by distorted? In the first lecture, I have shown in the waveform, Fourier series analysis. Okay, I think probably lecture 2 or lecture 3, you can recollect that. So because of that distorted sinusoidal flux in the air gap, this induction machine will operate with pulsating torque. This induction machine will operating with the pulsating torque. Who is the main culprit to operate induction machine to with operating with the pulsating torque? That is fifth harmonic component. Therefore, the rule of thumb is at any point of time, fifth harmonic component should not enter into the machine. Okay, so it will make the machine to operate with the pulsating torque. Therefore, at this point of interconnection, there should be a suitable filter which will eliminate that fifth harmonic component. Filter concept we will study in the later stage. Okay. Now you may have a question. We are in the rectifiers chapter, but why this fellow is giving induction machine is an example. Okay. There is a reason for that. For example, if you consider a single line diagram of a power system network, okay, a single line diagram of a power system network. Let me take, there is one switch over here. At the end, at the receiving end, there is a rectifier circuit. If you see the same diagram in the power system subject, they will say that this particular load as non-linear load. Okay, non-linear load. The reason is this particular load, basically rectifier bridge, will make the waveforms to be non-sinusoidal waveforms. Hence, it is referred as a non-linear load. This is a three-phase single line diagram. Okay. Now, what is the point here? Follow carefully. This is one practical example. Let us say a three-phase induction motor is connected at this PCC. What do you mean by PCC? PCC stands for point of common coupling. PCC stands for point of common coupling. That means it is a bus where different types of loads or different systems can be connected at one particular bus. Okay. Now, what is the point here? Whenever this switch is open position, it is noted that induction machine is operating normally. Okay. If switch is open, induction motor is operating normally. Okay. Suppose if that switch is closed, induction machine is operating with pulsating torque. Okay, induction machine is operating with a pulsating torque. Think about what could be the reason for that. Okay, what could be the reason for that? The moment when you close this switch, this three-phase bridge rectifier is coming into the power system. Later on, we'll study that. Of course, we entered into three-phase rectifiers. In this chapter, we'll show that this three-phase bridge rectifier will introduce 6K plus or minus 1 harmonics into the source side. Okay. Because of that, 6K minus 1 harmonic, it will disturb the load. Therefore, this induction machine will operate with a pulsating torque. Okay. Therefore, what is the suggestion from our side? You should place one filter LC circuit at that point of common coupling. Okay. In our earlier inductors and capacitors lecture, the skill assessment problem, I gave one question. Draw Bode plot for this LC circuit. If you draw Bode plot for this LC circuit, then you can understand the filter concept. Okay. If you not tried, at least try it now. By the end of this rectifier chapter, we'll enter into the choppers chapter. At that time, we'll discuss this filter concept, right? Now, at this stage, I can tell you that what is the problem with the fifth harmonic component and how to mitigate that by using a fifth harmonic filter. How to, what is the filter concept, that we will study in the choppers chapter. Chapter to chapter, there is a link. Okay. So, from this overall discussion is, whenever harmonics are presented or harmonics are injected into the grid, the loads will operate with the so here the conclusion is, whenever this three-phase power electronic circuits injected harmonics into a power system grid, the loads will operate with a performance a little bit deviated. Therefore, we should be careful enough that the harmonic content should be reduced to accepted levels either by filters or suitable PWM circuits. Now, with this introduction, let us start the first circuit in three-phase rectifier circuits. The circuit title is three-phase half-wave uncontrolled rectifier. Okay. So there are two configurations here. The first circuit is named as common cathode configuration. The second circuit is named as common anode configuration. We know the properties of these two circuits. Common cathode configuration, that is, the device connected to higher positive potential only will forward bias. Remaining devices will be reverse bias. We will use that property. In common anode configuration, the device which is connected to higher negative potential only will forward bias. Remaining devices will be reverse biased. That is the basic concept. Anyhow, before looking into the waveforms, first let us try to understand the source property. Source voltage is based on phase voltage waveforms. VAO is equal to VMP sin omega t. VBO, VMP sin of omega t minus 2 pi by 3. VCO, VMP sin of omega t plus 2 pi by 3. Okay, this is what source voltage equation. Now, if you draw that waveform here, first, before going into the analysis, first let us try to understand what is this source voltage property. Now, follow carefully here. The blue color waveform, right? The blue color waveform is a reference, that is VAO. So, this is this instant is pi and this instant is 2 pi. Okay. And here this instant is pi by 2 and this instant is 3 pi by 2, right? That is a 3 pi by 2. Now, the entire cycle I divided into 12 equal parts. 12 equal parts. That means angle at this point is 30 degree. This point is 60 degree. This is 90, 120, 150, 180 and so on. Like that you can divide the waveform. Okay, next. The first observation is at omega t is equal to 30 degree. Follow carefully. You need to draw the waveforms with your hand, then only you will understand the concept. At omega t is equal to 30 degree, I can notice that positive side, upper half, VAO blue sinusoidal, VCO black sinusoidal, both are crossing each other in the upper half. At that instant, lower half VBO red color sinusoidal has negative peak. Okay, I am repeating. In the positive half at 30 degree, blue and black are crossing each other. At that instant, red one is having negative peak. Next. Now see at this instant, this is a 150 degree instant. At 150 degree instant, VAO blue one, VBO red one, both are crossing each other. At that instant, black one, VCO has negative peak. Next, at 270 degree, VBO and VCO, black and red, are crossing each other. At that instant, third phase voltage VAO blue one has negative peak. I am repeating. At omega t is equal to 30, 150 and 270 degree, any two phase voltages are crossing in the positive half. At those instants, third phase voltages have negative peaks. These 3 points, what are these 3 points? 30, 150 and 270 degree. These 3 points are named as positive phase crossover points. Okay, let me write down that statement here. Positive phase crossover points. Positive phase crossover points. Okay, what are that? Omega t is equal to 30 degree, 150 degree and 270 degree. Okay, yet omega t is equal to 30 degree, 150 degree and 270 degree. Any two phase voltages are crossing in the positive side. Third phase voltages have negative peaks. Therefore, these 3 points are named as positive phase crossover points. I hope it is clear. In the similar line, now let us look into negative half. At omega t is equal to 90 degree, I can notice that red and black are crossing in the negative side. At that instant, positive side blue color waveform has positive peak. VAO has positive peak. Next, at this point, this is a 210 degree. Okay, at 210 degree, blue and black are crossing in the negative side. At this instant, red one VBO has positive peak. Next, this instant 330 degree. At 330 degree, blue and red has crossing in the negative side. At that instant, black one VCO has positive peak. I am repeating. At omega t is equal to 90 degree, 210 degree and 330 degree, any two phase voltages crosses in the negative half, negative side. At those instants, third phase voltages have positive peaks. Therefore, 90 degree, 210 degree and 330 degree, These 3 points are named as negative phase crossover points. Let me write down here. Negative phase crossover points. Negative phase crossover points. Okay, what are that? Omega t is equal to 90 degree, 210 degree and 330 degree. Okay, negative phase crossover points are 90 degree, 210 degree and 330 degree. So by using these properties, let us interpret these circuits. Let us take first circuit. Now what is this first circuit property? D1 will be forward biased whenever phase A is more positive. Okay, D1 will be forward biased whenever phase A is more positive. So under that condition, D1 will forward bias and turn on. When D1 is turned on, you can say that load terminal X will be connected to source terminal A. Therefore, voltage across XY terminals will be same as voltage across AO, right? That means if D1 is on, output voltage will be same as VAO. Okay. Next point. D3 will forward bias when phase B is more positive. So when D3 is on, X will be connected to B, hence V0 is equal to VVO. In the similar lines, D5 is connected to source terminal C. D5 will forward bias whenever phase C is more positive. So under that condition, X terminal will be connected to C, hence V0 will be same as VCO. Okay. Now the next question is, under what conditions phase A, phase B, phase C are more positive? Okay. Now look into the source voltage waveform. I can say here from 30 degree to 150 degree. So this instant I can write 30 degree and here this instant as 150 degree. So from 30 degree to 150 degree, notice here phase A blue color sinusoidal is more positive than other two. Okay. Therefore, we can write here D1 will be in conduction. 30 to 150 degree, D1 will be in conduction. If D1 is in conduction, just now we told that output voltage will be same as that of VAO. Okay, output voltage will be same as that of VAO. Next, from 150 to 270, from 150 to 270, I can notice here phase B is more positive. Therefore, D3 will forward bias. Because of diode, it will start conduction. So if D3 is in conduction, output voltage will be equal to VBO. Okay, output voltage will be equal to VBO. Next, 270 to this point, 390 degree. VCO, black sinusoidal, is more positive and hence D5 will forward bias and it will be in conduction. When D5 is on, output voltage is VCO. Output voltage is a VCO. Okay. Now here 360 to 390 is same as 0 to 30. Okay. So 0 to 30 also D5 is in conduction, hence output voltage is equal to VCO. Okay. So in three-phase rectifier circuits, especially, it is not advisable to draw output voltage waveform straight away. Before that, it is good to draw this type of diagram. This is called conduction sequence diagram. It will give you during what interval, what are the devices in conduction, what is the corresponding output voltage. Okay, so it is easy to draw output voltage waveforms if you have this type of conduction sequence diagrams. Okay, once you have this diagram, the next step is very simple. You need to look into the corresponding source voltage waveform and then plot at the load side and then plot at the load side. So now I am going to draw output voltage waveform 30 to 150 degree. Just have a look at source voltage. Okay, just have a look at a source voltage. VAO waveform, the blue color sinusoidal is like this. Okay, the blue color sinusoidal waveform is like this. If you just draw this particular portion at the load side, you will get a V0 waveform something like this. Next, from 150 to 270 degree, VBO, the red color sinusoidal is like this. The red color sinusoidal VBO is like that. Next, 270 to 390 degree, VCO, that is a black sinusoidal. It is like this. VCO, black sinusoidal is like that. Now, 0 to 30 is the same as that of 360 to 390. That is a black one. This is what VCO waveform. Okay. So this is the output voltage waveform for first circuit. If you give the three-phase balanced source voltage at the output side, you will get V0 waveform like this. Next, let us draw output current waveform by considering load as resistor. Let us draw output current waveform by considering load as a resistor. We know that from single phase rectifier analysis, what we discussed, for a resistive load, output current waveform is just similar to output voltage waveform. Okay. Therefore, output current waveform, it is just followed by output voltage. The only difference is magnitudes. Just divide with the resistance, you will get output current waveform for a resistive load. Therefore, this is how V0 and I0 waveforms. V0 is already plotted. Now this is a output current waveform. Okay. So most of the textbooks will not show these two waveforms separately. Only one waveform is represented, and I0 is also just like that. Okay. First time we are drawing all the waveforms just for understanding. Now, for example, if you draw output current for inductive load, now follow carefully here. Whenever we have inductive load, especially in the three-phase circuits, let me write here inductive loads. Especially in the three-phase circuits, as the pulses are coming immediately, we can say that there are very rare chances for discontinuity. And for the analysis to be simplified, we can assume load current is a ripple free. In case of three-phase rectifier circuits, just for analysis is to be simplified, output current waveform will be treated as ripple free. Okay, so in the three-phase circuits we will not going into discontinuous conduction cases. Okay, because chances of discontinuity is very rare, because as the number of pulses are coming immediately, we may not have discontinuous conduction. So these three waveforms these three waveforms are treated for common cathode configuration. These three waveforms are treated for common cathode configuration. Now, let us look into second circuit. Second circuit is common anode configuration. What is its property? The device which is connected to higher negative potential will forward bias. Remaining devices will be reverse biased, right? Now see here, D4 is connected to phase A. So D4 will forward bias whenever phase A is more negative. So when D4 is forward bias, directly you can say that it will turn on, hence X will be connected to A, so V0 is equal to VAO. Let us draw simultaneously here. VAO, blue color sinusoidal, is more negative from 210 degree. So this is a 210 to 330. Okay, 210 to 330. So you can write D4 is in conduction. When D4 is in conduction, output voltage is equal to VAO. Output voltage is equal to VAO. Next, D6 is connected to phase B. Hence, D6 will forward bias when phase B is more negative. Therefore, when D6 is on, this X is connected to B, hence V0 is equal to VBO. So, now check here, VBO is the red color sinusoidal. VBO is more negative from 0 to 90. Hence, in this interval, D6 will conduct. Okay. When D6 is on, output voltage is VBO. Output voltage is VBO. Again, D6 will conduct from 330 to 450. This is 450 degree. Okay, that is a 450 degree. So in this interval, D6 will forward bias. Hence, output voltage is VBO. Now, D2 will forward bias when phase C is more negative. So phase C means black sinusoidal. So phase C is more negative from 90 to 210. Therefore, here D2 will conduct. And in this interval, output voltage will be VCO. I am repeating. D4 will forward bias when phase A is more negative. Under that condition, V0 will be same as VAO. That is from 210 to 330. Next, D6 will forward bias when phase B is more negative. Under that condition, V0 is equal to VBO. VBO is more negative from 0 to 90 degree and 330 to 450 degree also phase B is more negative. D2 will forward bias when phase C is more negative. Under that condition, V0 is equal to VCO. So phase C is more negative from 90 to 210. In that interval, D2 will be in conduction and hence output voltage is VCO. Now, by using these conclusions, let us draw output voltage waveform. Let us draw output voltage waveform. Now, just look at the source voltage. Okay, just look at the source voltage and draw the corresponding waveform shape. So this is a output voltage waveform I am going to draw. So in this interval, first let me start with the VCO. 90 to 210 VCO waveform is like this. Okay, 90 to 210 VCO waveform is something like this. Next, 210 to 330 VAO waveform, that is a blue sinusoidal. It is like this. Okay, 210 to 330 VAO, that is a blue sinusoidal. 330 to 450 VBO, that is a red color sinusoidal. It is like that. Okay, 0 to 90 VBO, this is not a full pulse, it is just 90-degree pulse. Remaining these three pulses are 120-degree duration. Follow carefully. This is what the output voltage waveform for, just for reference, let me write down here. This is the output voltage waveform for CC configuration, and this is the output voltage waveform for CA configuration. Okay, CA configuration. So in these two waveforms there are some similarities and some differences. First, let us discuss about the similarities. These two waveforms contains 3 pulses for one cycle. Okay, one cycle means 30 to 390 here one cycle, 90 to 450 here, that is one cycle. You have to talk about for 360-degree span, and each pulse duration is 120-degree. Those are the similarities. What is the difference? This particular V0 waveform is completely above x-axis. This V0 waveform is completely below x-axis. Therefore, if you calculate area under these two waveforms, you will get same area. Okay, that means DC magnitude is same. But what is the difference? This waveform will have average value of positive magnitude. This waveform will have average value of negative magnitude. Therefore, there is no need to find average values separately. Any one waveform is enough to take a minus of that will give you second waveform. So with this point we can calculate average output voltage for only CC configuration. Okay, just remember. So with this waveforms completed for this particular circuit. Now before moving to the equations, there is one more point. Now just look this circuit closely. Okay, look this circuit closely. Now for example, if D1 is on, follow carefully. If D1 is on, what is voltage across D3? Anode of D3 is connected to B, then cathode of D3 will be connected to source terminal A. So I can say here anode to cathode voltage for D3 is VBA. Okay, next D5, anode to cathode voltage for D5 is VCA, right? So what do you mean by that? When D1 is on, voltage across D3 is VBA and voltage across D5 is a VCA. If you want, let me write down one particular combination. If D1 is on, voltage across D3 is equal to VBA, voltage across D5 is equal to VCA. Voltage across D5 is equal to VCA. In the similar line, I will suggest you to try it out. When D3 is on, what is voltage across D1 and D5? If D3 is on, I can say voltage across D1 is VAB. Voltage across D5 is VCB. Similarly, if D5 is on, what is voltage across D1? That is VAC. What is voltage across D3? That is VBC. Now observe carefully here. When one particular device is on, Other two devices are subjecting to BA-CA, BC-AC, CB and AB. These values are line voltages. Therefore, in this particular circuit, half wave rectifier or full wave rectifier also will have same conclusion. When one device is on, let me write down a statement here. When one device is on, other devices are subjecting to line voltages. Other devices are subjecting to line voltages. Therefore, from this we can say that peak inverse voltage for a particular device is equal to VML, peak value of that particular line voltage. Okay. So, in this particular source voltage notation, we have phase voltage representation, right? We have phase voltage representation. We don't have line voltage waveform information. Therefore, just for time being, we will not draw voltage across any device. Okay. Later on, we will take line voltages as a reference. At that time, we can take or we can draw voltage across devices also. Okay. Just for time being, we will just postpone. Okay. I am not escaping. I am just postponing. In the later lectures, we will draw voltage across a device wherever line voltage information is available. At this stage, we have only phase voltage information. We will not draw at this moment. Now let us look into some equations. As I told, we can write down the equations for any one configuration. Let me take that for common cathode configuration. So the first one is average output voltage. Okay, average output voltage. V0 is equal to 1 by periodicity. 1 by periodicity. If you look into this waveform, we can notice that the periodicity of this repeated waveform, repeated pulses, is 120 degree. Therefore, periodicity denominator you should take 2 pi by 3. What are the limits for this particular blue color pulse? That is from 30 degree to 150 degree. Therefore, in the average output voltage equation, we can write it like this: 1 by 2 pi by 3 integration limits pi by 6 to 5 pi by 6. We have blue color sinusoidal, that is VAO. What is the equation for VAO? That is VMP sin omega t d omega t. Okay. Therefore, let us simplify this. 3 VMP divided by 2 pi integration for sin omega t minus cos omega t limits pi by 6 to 5 pi by 6, 30 to 150. Okay. Now, let us simplify this. 3 VMP divided by 2 pi minus cos 5 pi by 6 minus of minus plus cos pi by 6. Now here cos 150 is nothing but minus root 3 by 2. Therefore, this value I can write it as root 3 by 2. Cos 30, this is also root 3 by 2. Therefore, these two summation will give you root 3. Hence, average output voltage is equal to 3 root 3 by 2 pi into VMP. V0 equation is 3 root 3 by 2 pi into VMP. Okay. Now, for example, if load is resistive, then we can write average output current is equal to V naught by R. If the load is resistive, we can write average output current is equal to V naught by R. If the load is inductive, as I mentioned earlier, in three-phase rectifier circuits, we can treat that load current is constant. We can treat that load current is a constant. Suppose if the load is mentioned that RL load, you can take I naught is equal to V naught by R. For RLE load, V naught minus E divided by R. Most of the cases, constant current load means I naught value will be given in the data itself. Okay, no need to worry about it. Now, coming to power delivered to the load. Even in the previous lectures also, students have a few doubts about it. Okay. Now, let us define basically what is the definition for power delivered to the load. So, for example, P naught is equal to 1 by cycle time, full cycle I am taking, 1 by 2 pi, integration from 0 to 2 pi, V naught multiplied with I naught d omega t. Okay. Now, for example, if the load is resistive load, if the load is a resistive load, in that case we can write I naught is equal to small v naught by R. Now follow carefully where I am using small letter, where I am using capital letter. That is very important. Therefore, P naught, average power delivered to the load, capital P naught, is equal to 1 by 2 pi integral 0 to 2 pi. How can I write down? V naught multiplied with V naught by R d omega t. Okay. Therefore, it will give you 1 by R into 1 by 2 pi integral 0 to 2 pi V naught square d omega t, isn't it? Now, if you observe carefully here, the value inside this red bracket is nothing but VOR square divided by R. Therefore, we should calculate RMS voltage only for resistive load. Okay, only for resistive load. But for inductive load, we will get a conclusion little bit different. In case of inductive load, what is the concept? Average output current is constant. Okay, average output current is a constant. Therefore, we can write P naught expression something like this: 1 by 2 pi integration from 0 to 2 pi V naught multiplied with, now observe carefully, I am replacing small I naught with a capital I naught in case of inductive load, because load current is a constant here. Therefore, if you take capital I naught outside from the integration, the remaining integration you can call it as a average output voltage. This is the main reason, if you recollect in our rectifiers chapter previous beginning, voltage to float, currents to float, in the table I mentioned that for resistive load output power can be calculated with VOR square by R, and for constant current load we should calculate with V naught into I naught. Both of these are average values. That is the basic fundamental reason. Now, if the load is resistive load, R load, let us calculate RMS voltage first. VOR square is equal to 1 by 2 pi by 3 integral pi by 6 to 5 pi by 6 square of the function Vmp square sin square omega t d omega t. Vmp square sin square omega t d omega t. Okay. Now 3 Vmp square divided by 2 pi integral pi by 6 to 5 pi by 6 sin square omega t can be written as 1 minus cos 2 omega t divided by 2. Integration is with respect to omega t. Okay. Next 3 Vmp square divided by 4 pi integration for 1 is omega t minus cos 2 omega t integration sin 2 omega t divided by 2 limits pi by 6 to 5 pi by 6. Okay. Next 3 Vmp square divided by 4 pi. Now upper limit minus lower limit. 150 minus 30 will give you 120. Can be written as 2 pi by 3 minus half into upper limit sine of 5. This is a 5 into pi by 6 multiplied with 2. Therefore I can write it as 5 pi by 3. In other words 300 degree minus lower limit will give you pi by 3. Okay, will give you pi by 3. Now if you see here sine of 5 pi by 3, that is sine 300, I can say this value is minus root 3 by 2 and this value is root 3 by 2, that is a sine 60. Therefore what is the value inside this curly bracket? That is minus root 3. So let me write down here. So 3 Vmp square upon 4 pi into 2 pi by 3. Now this value is minus root 3, right? Minus into minus plus root 3 by 4. Okay, I'm sorry, this is root 3, this is 2 here, root 3 by 2 only. Okay, root 3 by 2. Therefore now final conclusion is VOR is the required value, RMS voltage. You need to take a root of this function. Okay, so Vmp square, if you take a root, then it will give you Vmp 3 by 4 pi into 2 pi by 3. 3 and 3 will get cancelled out. 2 pi by 4 pi will give you 1 by 2. Okay. Next plus 3 root 3 divided by 8 pi under root. You have to take a root for that function totally. If you check in the calculator, you will get this numerical value as 0.891 Vmp. Okay, 0.891 into Vmp. So in the exams where calculator is not allowed, you can memorize this value and accordingly Vmp whatever value is given, you can use that. So this is about 3-phase half-wave uncontrolled rectifier analysis. With this I will conclude this lecture. Thank you.